So the topic is speeding up inference with fast KV movement. And how do we do that? Is to make Ethernet carry KV or make it lossless, even though inherently it's lossy. So there are two kinds of inference systems today. You can think of the mainstream, where there's a whole bunch of prefill and decode done in a single or two GPUs, and they're not disaggregated. And the storage is typically external and accessed through the front-end network, which is lossy Ethernet. So typically, a lot of TCP type traffic that's moving on that front-end storage. In addition, the storage traffic is also using TCP. And the question is, can we make this front-end accommodate inference in a high-speed sort of way? And the second one is I'm going to call it large-scale enterprise. Here, prefill and decode are disaggregated. It's getting more common, certainly as sizes have grown. And here, you have the ability to use the back end as well as the front end. And the question is, can we do this? And in that case, which flow would you want to send on what network, and how do you prioritize it? Okay? And so those are the topics of this talk. So I'm going to show you here what a day in the life of an inference request looks like. So there's a demo which we can show you after this of this exact system. These are AMD servers. So you see now this request just got served. Another request is going to go. So let me walk you through that. A second request is going to come out of the request router, which is vLLM in this case. And it's going to be sent to one of the nodes where first KV is fetched and prefill is conducted. And then KV is pushed back and sprayed back out to the servers out there. And decode is taking place right now. And that continues over and over and over again. Okay? So when we ask for service from these nodes, that's what we get. And the major tension here is that inference wants both TCP and RDMA. Because how did this request come? It's from the outside world as an AI inference cluster. And that cluster wants to bring TCP, and then you need also access to the inference store. And inference likes to go on RDMA because it's not just lossless, but the DMA makes it really fast. And you want both. But TCP and RDMA basically hate each other, because TCP likes to run buffers on full to get congestion signals, and RDMA wants the network to be lossless. And so we try to run RDMA on a TCP network where there's no ECN marking or there's no DCQCN type congestion control turned on, then RDMA will look like UDP from a TCP perspective. Okay? So it's congestion insensitive. That's the problem. So either you build yourself two fabrics, which nobody wants to do, or you dedicate a Rocky V2 priority in your Ethernet on the wires, then you take on all the data center bridging standards. Okay? It's not exactly easy. It can be done, it's been done, but people generally don't want to do it. So the question for us is there are two. First is, can we make the front end support both TCP and RDMA? And you see the answer is yes, okay, based on some things we've done. And the second is, can KV transfers be prioritized? So I want to prioritize KV reads. KV read is when a GPU is saying, I want to get KV. Decode node, if it's disaggregated, says, I want to get KV. Or the prefill node says, I want to get KV from the store. And that's a KV read, and you don't want to slow that down because the GPU is going to idle. KV writes. So I want to write this KV, or I want to transfer KV from a GPU node to storage, so some other node may want to use it, like decode, for example. And KV demotions, these are like evictions. You're going up and down the cache hierarchy, so you don't have to really do that promptly. So you want to deprioritize that. But how does this work in a network which doesn't understand priorities? Okay? So that's more crisply the sort of questions we want to get to. And we need always, if you're not going to use conventional techniques, you need some kind of a hook, some kind of an ability or enabling technology. And that's what this is. So we wrote this paper in 2018, and it's a way of synchronizing clocks at least as accurately as PDP, if not more, but it doesn't need any network support. It's purely software-based. It's end-to-end. It can work in public clouds. It can work across the world, et cetera. Happy to show a demo of that also if you're interested, but that's something we can do, right? And you can use that to do congestion measurement. Once you have synchronized clocks, if I know when a packet left here and I know when it got there, and these two clocks are synchronized sub-microsecond accuracy, I can determine congestion on the path. Once I understand congestion without the network signaling it to me through ECN marks or some other way, then I can control it. I can eliminate it. Okay? So how does this work? It works by using shims. Okay, so again, we don't want to take any hardware support, or we don't want to make the application become aware of us or the network underneath us. So shim, in the every RDMA application, when it starts pumping packets, we intercept the queue pair creation events. So first, we'll synchronize the clocks. And secondly, we will intercept the queue pair creation events, the shim will. And then we'll send the shadow probes, this dotted line. It'll have the same queue pair label, so it'll follow the same path as the data packets, and we can get one-way delays and good put. And then when we detect congestion, the one-way delay is exceeding a threshold that bigger than propagation time, we will send a congestion notification packet. This is the QCN standard, which is every RDMA NIC understands. And then finally, if we're not happy with the path we're on, by swapping queue pair labels, we can get to a less congested path, because we've been probing other paths for how their one-way delays look like. Okay? So far so good, I hope. And the point is that this is transparent to both the applications on top of us and the network underneath us. So we don't need the network to do anything special. Okay? So the other thing to say is that shim fits very neatly onto smart NICs. In fact, both the software and the smart NIC versions are being deployed at scale in a very large hyperscaler. And then let's look at this in-network congestion. I want to show you the mechanics of it. This is one thing to say I'm measuring congestion using clocks. How do we do this? So what happens if you try to DMA traffic over an Ethernet droppy network today without any congestion control? You will have the problem that this GPU is sending it to the receiver on the right-hand side, and on the path, half the link's bandwidth is taken by some cross traffic. Of course, the sender doesn't know this, so it'll keep sending, and then some switch buffer will fill up and eventually overflow. And RDMA is terrible at sustaining losses because it's expecting a lossy network, so otherwise it'll have to go back in and something costly. So its good put will suck. So that's what will happen if you try to send traffic on a DMA traffic across a network, which is not lossless. What we can do with the shims are present is synchronize the clocks, as I mentioned earlier, send the same traffic, keep measuring the one-way delays, right? Sender and receivers are going to be measuring the thing on the right as one-way delays. If that's getting bigger, then you can send this congestion notification packets and to the particular rate limiter in this transmitting NIC, because you have the flow label of the queue pair. Okay, that's what you can do, control the traffic. Okay, and so this is in-network congestion. You can do more than that if you have receiver-side incast. One-way delay-based signaling also works, but you can do better because so many senders may blast into you. If I'm a storage server, then multiple GPU nodes may be trying to store the KV with me, and I'm getting blasted into, and I want to find a better way of pushing back. So this situation is similar to the one before, and multiple senders are ganging up on you, and then you're going to be hurting. So in this case, what you can do is use this device, which we call the ghost buffer. So I implemented this device, the early version of this, in the Cisco's Nexus 5000 switch. It's called the proxy queue there, but it was inside the hardware. This is purely a software widget. And actually, I heard about this when I was in grad school. It's called a virtual buffer in the mid-90s, so it's a nice idea. What it is that the ghost buffer measures the bytes that come off of the wire. You increment the counter by the bytes that come off of the wire, and then you decrement it at a steady rate that's slightly less than the actual line rate. So it's a rate estimator modeled as a queue. So the bursts can be taken out. Okay? So now what happens is, in the same scenario the senders are sending earlier, you can see the ghost buffer will fill up if the line hits 395 gig. Right? If the rate of incoming traffic is 395, so you can start sending congestion before the receiver line is filled up. Okay, that way you can hold up certain bandwidth headroom, which will keep the latencies really small. Okay, so it's a very powerful device and technique. You have to use both this and one-way delays because you don't know where the congestion is going to be. It's not necessarily going to be at the edge; could be in the inside. Okay, so this is like a canary in a coal mine, right? You folks know that you take miners take canaries into coal mines that keep squawking, and if you don't hear the squawking, you have to run out because the air just got bad, right? And these days you can think of this as Ozempic for the network. It's just letting the network know you're full, right? Don't eat anymore, okay? And so that's what the ghost buffer is. And so you can also use this to slice bandwidth. You can have gold, silver, bronze type priorities. You can slice how you want. So this is one way you can prioritize traffic. You can say KV reads, KV writes, whatever you want, okay? So with this sort of toolkit, let's go put it together and see what we can do in actual deployments, right? So this is something in Oracle Cloud. We rented 10 nodes. Actually, I should mention Kamran Ahmed, who's my collaborator, sitting over here in the front row. I believe you may have a demo to show. Maybe. Okay. So it's the last talk, and we may show a demo if you hang around, okay? So 4 pink senders sending the pink receiver, blue sender sending the blue receiver. The receivers can get up to 100 gig. And what's going to happen is there's receiver side in-cast congestion. I guess this is the light. So this is, this guy can get congested because 4 guys are trying to send to it. Similarly here, but there's also in-network congestion when the blue and the pinks are meeting inside. So this is sort of worst case thing. And the network, unfortunately, is plain. There's no PFC or DCQCN because these Oracle Cloud, public clouds don't have ECN enabled. And so in this case, when the senders are DMAing, both the receiving NICs are fully busy. They're getting 100% good throughput. They're busy. The per flow throughputs, if you add up, the pink guys together and the blue guys together will give 100 gigs. That's what's keeping the corresponding receivers busy. But then tons of packets get dropped on the network, so the good put, the effective number of new packets delivered is only 25%. So you can see here, this number is 20 gig on a 100 gig line, and what was attempted to send was close to 80 gig, okay? What's getting through is no more than 20 gig. That's the amount of dropping there is. As you can see here, this is all the drops that are happening, and this is how bad the delays are, right? So, terrible. Then you turn on this one-way delay control for in-network and ghost buffer for the edge. We sacrifice just 2 gigs on the line, so 2%. You might see, if you're close enough or even from far, this line is slightly shorter than that line. So just 2%. That's what it looks like. Can't even tell. But the fairness is fully achieved. Good put is 100%, meaning everybody gets 25 gig, blue senders and pink senders alike. And delays are down to steady, less than 20 microseconds. And so this means you can really, really run the network buffers at very low occupancy without underrunning the links. Right? This is sort of the interesting magic that's going on, right? And the outer sequence errors are all gone because no packets are dropped. Okay? So this is what you can do with RDMA on a plain TCP Ethernet network. And this is in the cloud, so there may be TCP traffic running in the background. Okay? We don't care. And so let's just specialize to RDMA senders and look at the slicing of the bandwidth. In this case, blue and green senders have been allocated 75 and 20 gig each. And the key thing I want to show are 2 things. One is that the bandwidth is sliced as allocated. So, oops, I went ahead. So when blue and green are present together, they get the rates they're supposed to get. When only one of them is present, either blue alone or green alone, they get all 95. Okay, so this is work conserving. What you carved out for a blue or a green sender is not exclusively for them. If the other guy isn't there, then you get everything. That makes sense? So you're not wasting bandwidth on the wire. That's what I mean by work conserving. Okay, so let's get into KV, how all this combines to give us the sort of benefits we're hoping to get. So again, this is the first case, the first of the 2 cases, right? This one. And here, the stack is inference clients coming from the outside world. There's vLLM that does the scheduling, batching, et cetera, and LM cache, which handles the DRAM in the host, and Mooncake, which does the transfer or KV across the different memory hierarchy as well as to remote storage. And our shim is underneath that, okay? And we're going to use, in this case, the front end only, because prefill and decode nodes are they are not disaggregated, okay? And so this is the same thing as I showed you earlier. And here, what you are seeing the results. So what happens if TCP alone on this network transferring KV? And the y-axis is time to first token measured in seconds. And this is a workload where the requests are 48 kilo tokens at the prompt, the original prompt that comes in, and the 96 users loading the system. Okay, that detail is the next slide, I guess. So if you look here, the time to first token kind of all over the place. Same thing happens if you try to RDMA without protection from drops. And that's this blue line. It's even worse. And finally, if you put the shim on and control traffic, like I mentioned, on the same Ethernet. This is on the public cloud, by the way. This is Oracle Cloud, AMD rentals. And so you can see it's pretty hugging the x-axis. Mean has gone down, variance is taken down. And if you want to know the exact percentiles, you can look here. TCP, blue is RDMA without the shim, and green is the shim, RDMA with the shim. And you get improvements in the range of 8 to 12x for over TCP and 4 to 17x. You can see the bars. I mean, they're smaller fine print numbers that show you the exact multiples. This is for the time to first token, right, which is a key metric in inference. The second thing is, again, actually the details on what I was saying are up here. 96 concurrent users constantly loading the system, 48K context. And this is the end-to-end latency. This is the time from the first, this is a multi-turn agentic system. So the requests are coming continuously, and then you keep going, and then from the time you started to the time you finished, what was the whole thing? And it's shown here to be these numbers, okay? And then this is RDMA control, where you have mixed contexts. This is typical where it's not all short or all long, it's always mixed. And so what happens in that case is, what you're expecting to see is the short guy, because he's short, should be getting through earlier than the long guy. That just seems the obvious way that things should be. But because these TCP and RDMA without the shim lack discrimination, they actually do the opposite, okay? So first of all, you'll see the numbers in terms of improvements are here in the bar charts. They're summarized on top, okay? The unfairness I want to point to is this thing. You see here, the bars on the left are supposed to be shorter than the bars on the right. Perversely, some of them actually taller. TCP is barely almost equal. But what you want to see is what the green stuff is showing. The longs are almost exactly twice as long as the shorts, okay? And that's what you want to see, because that's how much bigger the prompts actually are, okay? And why is this happening? Okay, why is TCP unable to do this? What's going on here is the ghost buffer is doing the work. We've just given up to some small percentage, so there's no queuing. So shorts tend to go without seeing the longs. That's what's going on here, okay? And so this is the corresponding thing from the end-to-end. In the interest of time, I think the slides will be posted, so I'll move on to the last thing where prefill and decode are disaggregated. And so here the backend comes into play, the same stack as before, but prefill is on the left and decode's on the right, and you're going to go across. And these requests are flying in from the left, right? And the storage is still over there on top. And this is the front-end Ethernet, okay? So here, the similar numbers, time to first token, you're improving by these factors. And the reason it's smaller is because the transfer of what was happening before is when prefill got done, it was not necessarily handed off to decode sometimes. It would go and come back. Here, it's going to decode. As soon as prefill finishes, it goes to decode on the back end, okay? You get a less congested, beefier 400 gig NICs, okay? So whereas in the front end, it's 150 and 100 gig NICs, 100 on the GPU side and 50 on the storage side, okay? So you have an asymmetry, but that's what's happening. It's still 2.5, 3x improvements are not small, okay? Especially the higher percentiles, you get bigger improvements, which is where the action is. Finally, this is the end-to-end story. Here, again, it's multi-turn, and then sometimes the agent doesn't come back multiple times. So again, there are improvements, but more modest, okay? And we're playing with larger size clusters and, more, we haven't sliced the bandwidth from, prioritized and stuff like this. That's ongoing work. And so more coming shortly. So to conclude the talk, it is necessary to deliver KV fast, we all agree. and otherwise the GPUs are going to be idling. And front-end network's always been this terrible, nobody wants to go on the front end because it's like, nothing good comes of going on the front end. You get dropped. Okay, it's time to stop dropping packets. Let's create some headroom in the bandwidth, right? I'm speaking like somebody who's doing good to the world, okay?
Well, you are.
No, I mean, packets, I hear packets screaming out there, getting dropped, and the indignity of it. Okay, anyway, so in future, what we'll do is, we'll also do predictable bandwidth slicing, so you can actually see even more predictably in shorter and shorter completion times. Okay, so with that, I'll stop and take questions either here or there, and then for those of you who want to hang around and see a demo, Kamran's got something to show you. Thank you.